the first propagation step of chlorine to the first propagation step of bromine. So we'll do chlorine here and bromine here. For the reaction with methane, this is energy, right? And this is reaction coordinate. Right? We're just going to graph that first transition state. So we start at 0. I'm going to go back and check my notes. We went up to +1. And we went through some activation energy barrier of 4 kcals per mole. Okay? So this is the enthalpy of reaction. It's +1. We calculated that. And I just told us 4 kcals per mole is the activation energy barrier to get us over. We have to get over this barrier to get to here. For bromine, it was different. We still start at 0. Our ending point is 16. All right, so we have to get up to here. And when we draw this transition state, it just has to be a hump that's taller than 16. That's it. That's as precise as you have to be. And we just said that the activation energy barrier here is 18 kcals per mole. There's a very big difference in activation energy barriers between these two. And this is actually the real basis for the selectivity difference between chlorine and bromine. Chlorine, to get the reaction going, does not require a whole heck of a lot of energy to go uphill. We can figure that out, which bonds are different between these two reactions in the first propagation step. The breaking of the carbon-hydrogen bond is the same, but the formation of HCl versus HBr is different. And more energy is needed to get this particular reaction to work. So if we were comparing these two, we would say that this has a low activation energy. This one has a high activation energy relative to one another. Just relative to one another. No one in the room could disagree that this is bigger than this, right? This is bigger than this. There's no way of avoiding that. When we have a high activation energy in these types of radical reactions, so when we have high activation energy in radical reactions, the product or products is determined by the stability of the radical. When we have a high activation energy in radical reactions, the product or products is determined by the stability of the radical. Bromine has a very high activation energy. The product distribution at the end is solely determined by the stability of the radical. This is why bromine is so selective. The full rationale and relationship between this is called the Hammond postulate. We don't have time to go through it completely. We're not going to compare these things on an exam, but it's actually the activation energy of the bromination reaction. It's so high, so difficult to get us to here that once we do get here, whatever radicals we form, the most stable are the only ones that proceed forward. So when we have a relatively high activation energy, the product distribution or product is determined by the stability of the radical. The product in this reaction, if we can make a tertiary radical, that's all we're going to get. Chlorine has a low activation energy. This means it's less selective, it's very easy to make radicals, and it's more reactive. It's very easy to get here, forming radicals of all different shapes and sizes, primary, secondary, and tertiary. The energetic barrier to get to this point, where if we had propane or cyclohexane or methyl cyclohexane, it's very easy to make any radicals. And so in chlorine, we would make all of them. It's not very selective. Activation energy barrier is low. It means chlorine is more reactive. It reacts everywhere. If we have methyl cyclohexane, there's a tremendous activation energy barrier here, much higher than here. And so only the most stable radicals will form with this high activation energy barrier. We don't really have time to give this the full amount of time to digest in such a fast summer course. I'm intentionally truncating some slides about Hammett postulate theory. Don't want us to be confused anymore. But at the end of this, our energy calculations, hiding in them are these activation energies. And high activation energy processes are associated with less reactive species that then become more selective. Low activation energy processes are associated with highly reactive things. There's a small barrier here. The species will be highly reactive. It'll react everywhere. It'll be less selective. So in the end, don't fixate or be too frustrated about this understanding of Hammond theory or the simplified version of the Hammett postulate, but keep in mind that chlorine is much more reactive, much less selective. It goes everywhere. Keep in mind the very simple idea that bromine is less reactive and it's very selective. And it's less reactive due to this huge activation energy gap that has to get the process going. Okay, I think that's where we're going to wrap it up for today. There are a few more slides and a few more things I want to talk about, but they're not important. I've given you enough to work on today with calculations and these particular graphs, which you should be able to replicate the things in blue and red on these graphs. Not the activation energy. This was just part of our discussion about this, not the transition state, but really you should be able to take a very simple reaction. You could even imagine doing this with a molecule of ethane or maybe propane. You could try those types of things. You could take propane and try the propagation steps if you wanted a little bit of additional practice on this here. In your textbook, you can find a table of energy values, bond association energies in the radical chapter. You could imagine doing this calculation for the radical bromination of propane, where we make two different products. Make a secondary product, and make a primary product. You could actually try this on your own and use a table of bond association energy values, and you could actually calculate the energy for both processes. The enthalpy. What's the total enthalpy for this product? What's the total enthalpy for this product? What do the graphs look like? The way you set up this problem is there's two different types of hydrogens we're going after. So you'll need a primary approach and a secondary approach. These will each have two propagation steps. If you were setting this up, your first reaction would be looking at that breaking, right? And then you continue. And then you do the second propagation step associated with this reaction that leads to our primary product. And then there'll be delta H1, delta H2, delta H total that you could calculate. You could then graph it. You could then start the propagation step for the secondary position. The bromine radical. And you break this particular bond. And then you continue until you get all the way to the secondary product. And then you could also graph this. And what you're going to find is there's a difference in bond association energies between these two compounds. To make this primary radical is harder than to make this secondary radical. So this is the highest level you could practice on your own. I've set up this nice problem for you. It's quite complex, but this is how you could really practice this. After you've practiced methane a few times, you could then just simply grab a book and calculate the energy to make this compound and the energy to make this compound, and I've set it up very nicely for you here. I haven't done all the work for you, all the mechanisms or all the graphs or all the bonds broken, but as you work through this, you'll see HBr being formed, you'll see CH2 bromine bond being formed, you'll see a CH secondary carbon bromine bond being formed, and again, this energy value here will be a little bit different than that energy value there, so there's some slight differences in here, and this is a good problem to go through and practice, and you should see a energy difference between forming the secondary product, which is more favorable than the primary product. So this is the highest level you could take this to. If you don't have time to get to this level, definitely make sure you at very least practice the methane molecule that we worked on. Okay, there's about 4 or 5 minutes left. I'll take any questions to clarify or things, or I can stick around maybe